Hello everyone, this is Kevin from MBT. In this session, we're going to have a simulation on lithium-ion 21700 battery cell. As you can see, this is a cylindrical battery that consists of three different parts. The first part is the anode or negative tab. The middle part is the active zone or the jelly roll that consists of several rolls of different types of materials like lithium oxides, separator, and graphite. And the last one is the cathode or the positive tab. As you can see on the right side, it has a diameter of 21 millimeters and a height of 70 millimeters, and that's why it's called 21700. Here you can see different properties of different materials that we're going to use in the simulation. And among the most important properties are the density, specific heat, thermal conductivity. That for the active zone we're going to use a cylindrical orthotropic definition for thermal conductivity. And for other two materials, as the thermal conductivity is constant in every direction, we're going to use a single value. And the last property is the electrical conductivity. On the right side, you can see the geometric properties of the battery cell. The diameter is 21. The height of the active component is 64 millimeters. The height of the cathode is 5. The diameter of the inner hole which the jelly roll is formed is 2.3 millimeters. The height of the anode is 1 millimeter. The nominal capacity of the cell is 4.95 amp hour, and the reference capacity that the experiments are conducted in order to define different parameters for the MSMD battery model is 4.9 amp hour. So now let's go to the Ansys software and start the simulation. So now here we are in the Ansys software. Now we're going to drag and drop the Fluent solver. I'm going to name it as 21700 single cell. So we save the project. Okay. Now for the geometry creation, we're going to use the design modeler. Okay, so first we're going to create the middle component or the active zone. So we use the XY plane and create a sketch. We name this sketch as active component. Go to sketching and zoom in to reach a good region. Now we use a circle to create a sketch. We give it a diameter of 21 millimeters. So this is it. Now I should use extrude to create the active components. So we apply. For the active component, make sure that you use add material for the operation. The direction would be normal and the height would be 64 millimeters. So this is a view, and we click on generate. Now we have the active component ready, but it needs the inner hole, so we're going to use another sketch to create the inner hole. Go again to the sketching. We use another circle. You can also do it by only one sketch, as defining the two circles at the same sketch, but here we did it with two sketches. There will be no difference. So the hole diameter is 2.3 millimeters. So this is it. And now we're going to again use the extrude option, but here for the inner hole and for the operation we're going to use the cut material. The height would be the same, and we click on generate. So as you can see, we have the inner hole and the active component actually treated as a single material in Ansys software for the battery simulation, so we don't consider the rolls around this central hole, and we treat the whole material as a single material. So now we go to the second part, and that would be the negative component or the anode. So we're going to use the same XY plane. We create a new sketch. We give it a name as anode component. Go to sketching, create another circle, give it a dimension the same as the active component, and it is 21 millimeters. As you can see, it's on the bottom of the jelly roll. So for modeling, we're going to use the extrude option, select the anode component. Remember that for the active component we use the operation of add material, but for the negative and positive tabs, or the anode and the cathode, we should use the operation of add frozen, because the chemical reactions are only defined in the active zone or the jelly roll, and the tabs are not considered for chemical reactions, and those are only for conducting and for the current flow in the circuit. So we use the add frozen operation, and as this is the anode, it had a height value of 1 millimeter. But as you can see, we should change the direction as reversed. And now we can click on generate and have the anode component ready. I'm going to hide this sketch. So now we have the jelly roll and the negative component. The last part would be the cathode or the positive component, and for that we need to define a plane on top of the jelly roll. So we're going to use the XY plane as the base plane, and for the transform we're going to use offset from Z, and the value would be the height of the jelly roll, and that was 64. So you can see the plane is moved up to the top of the active component. And now we click on generate, and now we have the axis here. So on the plane we're going to create a new sketch for the cathode component, and then we go to sketching, create another circle with the same diameter, and that was 21. So now we're ready to extrude this. We select the cathode component sketch as the geometry. For the operation, make sure to choose the add frozen. The direction is okay. The height needs to be changed, and we make it to 5. And click on generate. So if we hide the sketch, that would be the 3 main components of the battery. We have the positive component, the active component, and the negative component, and all of them are in solid. And the last thing we need to do is that we have now 3 different parts. For the whole cell to be treated as a single cell battery, we need to select all these parts and form a new part. So now the cell would be treated as a one object. So this was all for the geometry creation in Design Modeler, and now we're ready to move forward and go to the meshing module and generate the mesh for this battery. So now we go to the meshing module and start generating the mesh. Okay, the geometry is loaded. For meshing, we're going to use an element size of 1 millimeter. And for the rest of sizing options, we use the default values. So we click on generate. Okay, as you can see, we have a structured mesh for the active component and a non-structured meshes for the negative tab and positive tab, and that's a quite good mesh for this battery cell. If you want to do mesh studies, you can choose different element sizes for the battery, but for now and our simulation, this is a good mesh. And now we can go to define different components and give name selections to the model. So first we use the volume selection option. We start from the active component, give it a name as cell zone. Then we select the positive component and we give it a name as tab P zone. And the last part would be tab N zone. Okay, as you can see, we have the name selections for 3 parts. The last thing to do is to define the tabs. So this is going to be positive tab or tab P. And this is going to be tab N or negative tab. So positive tab and negative tab. We save the project. And now we're going to go to the Fluent solver and start the simulation setup. So now you start the setup by launching the Fluent solver. We're going to use the double precision for higher accuracy and start the solver. It's going to take a while for the mesh to be loaded. Okay, as you can see, the mesh is loaded. Before starting the simulation setup, we perform the mesh check. So the minimum volume is positive and everything is okay. For the time, we use a transient simulation. And from the physics tab, we're gonna enable the energy equation so we can capture the temperature increase inside the battery. Then we go to models, and for the models we're gonna enable the battery model. Okay, it says that available material properties or methods have changed. Please confirm these values. Click on OK. And now, for the solution method, we're going to use the MSMD battery model. For the e-chemistry models, we use the NTGK empirical model. The nominal cell capacity, as we stated before, it's 4.95 amp hour. The C rate, we can keep it as 1. The minimum stop voltage, we define it as 2.5, and the maximum stop voltage, we can increase it to a value like 6. But here in this simulation, we're going to use only the minimum stop voltage, as we're going to conduct the discharge on the battery. Next, we use different components to define our conductive zones, but these are not available here, so we should go to the cell zone conditions and define our zones to solid materials. So the cell zone is now fluid. Define it as solid. The same for the negative zone. And the same for the cathode. Here we don't mind the material type here, because the next step before defining, after defining the MSMD battery model, we're going to define the materials and assign these materials to each zone. So for now, that's enough. We go back to the battery model, and now you can see that the components are available here. So for the active component, we have the cell zone, and for the passive components, we have the negative zone and the positive zone. For the electric contacts, we only need to define the negative tab, which is tab N, and positive tab, which is tab P. Before going on, we should print the battery system connection info, and we have the message here that end of the battery connection info, and we can see that the battery model is okay in terms of definition of different components. Next, we go to model parameters. Here for the initial depth of discharge, we use a 0 value, and for the reference capacity, we give it a value of 4.9 amp hour. For the U coefficients and Y coefficients, we're gonna use the parameter estimation tool. So for that, we click on parameter estimation. You can see that the testing battery's capacity is 4.9 as we stated here for the reference capacity. For the number of DoD levels, we're going to use a level of 10. And now we're ready to load. The capacitive fade effect is also enabled. Now we load the discharging files. So we go to our main folder. These are the discharge curves for different C rates from 0.2 C rate, 0.4 and 1.01. These discharge curves are plots of the discharge, the voltage of the value of the battery cell in time in a definite value of the temperature. So for example, in 300 kelvins we conducted several discharge operations and we have measured the voltage of the battery and we created these text files. So we select the discharge curves and click on OK. Now the parameter estimation tool can fit the parameters into the U coefficients parameters A0 to A5 and B0 to B5. So click on fit parameters. You can see that the numbers are changed according to the discharge curves that we have provided for the parameter estimation tool. So now click on OK. Now again click on OK to define the battery model. Okay, again we have the message of available material properties and that's okay. As you can see here we have the values for the U and Y coefficients and everything is defined, so we can go on and go to the material section. If you provided wrong data, wrong experimental data for the discharge curves, for example the value of Y coefficients would be negative or you get some infinity values for these coefficients. So you should revise your discharge curves and again use the parameter estimation tool. So for now it's okay and we can go on to define our materials. So we have different materials. Here 3 materials for the active component and 2 passive components. So we're going to use the aluminum, give it a name as active material and a chemical formula as A_M. For the density it would be 2560, Cp would be 1000, thermal conductivity, as this is for the jelly roll, we're going to use an option of cylindrical orthotropic. So the axis origin is 0, 0, 0 and the axis direction is along the z-axis. So for the radial conductivity we give it a value of 1, and for the tangential and axial conductivity values we give it a value of 25 and click on OK. And for the electrical conductivity we're going to use a defined per UDS option. So for UDS 0 we give the value of 1.19 e to the power of 6, and for UDS1 we give it a value of 9.83 e to the power of 5, and click on OK. So it says change or create mixture and overwrite aluminum, and we say no. So now we have the active material ready. Here again you can see that the jelly roll or the active component is along the z-axis, and that's why we used the direction axis of z for defining the thermal conductivity as a cylindrical orthotropic option. So now we're ready to move forward and define the second material for the anode, and we give it a chemical formula of N_M as negative component. Density would be 8030, CP would be 502.48. Thermal conductivity we give the value of 16.27, the constant value in every direction. And for the electrical conductivity we give it a value of 8.33 e to the power of 6. Select no again. Now we have the anode material ready. Now we use it for the cathode material. Give it a formula as C_M. The density would be 2719. CP would be 871. The thermal conductivity would be 202.4, and the electrical conductivity would be 3.541 e to the power of 7. And that's for the last material. The air would be as the fluid around the battery cell for convection. And now we're ready to go to the cell zone conditions and assign the materials to different cell zones. So these are the cell zones we have. That previously we changed the type from fluid to solid to have them in the MSMD battery panel. So for the cell zone we select the active material. For the negative zone we select the anode material. And for the P zone we select the cathode material. Next we go to boundary conditions. We only need to define the thermal boundary conditions. So the thermal conditions, we use a mixed heat transfer of convection and radiation. So the heat transfer coefficient would be 5.3. The temperature, we keep it as the free stream temperature would be 300. The external emissivity of The battery shell would be 0.8. The external radiation temperature would also keep it as 300 and the rest as 0, and click on apply. So you should define the same boundary condition for other walls, but here the type of wall, here we use the option of copy to copy the boundary conditions from tab N that we previously defined, and select all the walls and copy. So for example, if you go to tab P and check the boundary condition, we should see the mixed option of heat transfer. So now we move forward and go to methods. We use the simple form of scheme for the simulation, but for the user scalar 0 and 1 we choose a second order upwind to reach a higher accuracy. From monitors we create two report plots. The first one would be a surface report with area weighted average values of temperature. From the field variable we select the temperature and static temperature. For the cell zone we report the file, report plot, and print to console, and click on OK. So this is for the first plot. The second plot would be for voltage, and we give it a name as phi. Use the same area weighted average option. For the field variable use the battery variables, and for the variable definition use the cell voltage and click on the wall cell zone. Again, report file, report plot, and print to console, and click on OK. So we will have two report plots of temperature of the cell and voltage of the cell. So now we're ready to go to initialization. We're going to use a standard initialization form, and with a temperature of 300, as the free stream temperature was also 300, so we can keep that as initial value, and click on initialize. So initialization is done. We go to run calculation. We check the case for any recommendation. We have no recommendation from Ansys, and that's a good point. For the number of time steps, we use 80 time steps of size 50 seconds for each. For the reporting interval, we give the value of 5, and for maximum iterations per time step, we give the value of 10, and that's fairly enough for this simulation. And click on calculate. As the battery mesh size is not large, you can expect a very fast convergence of residuals. So here you can see that the residuals for continuity, and x, y, and z velocities are 0 because we have no fluid motion. We could also disable the equations for flow for faster convergence, but here that doesn't affect the simulation, and we can keep them. So we can see after the first time step we have the temperature report plot that shows an increase of the temperature over time, and for the cell voltage we have a reduction that defines the discharge behavior of the battery. So this was all for the modeling of cylindrical battery of type 21700. I hope you enjoyed this session. If you have any questions, you can always reach us by email. We look forward to receive your valuable comments and suggestions for further complex and useful projects. So I hope you find it well and have a good day.